I want to show you that the efficient simulation of quantum dynamics is not limited to local dynamics. I showed you on the previous slide that if the dynamics is local, then it's always possible, but it's not limited to local dynamics. In fact, you can show, and I will not prove this, but on your latest problem set for the holiday period, you have a little bit of more time, and you can think about that. There is a somewhat longer problem with various parts, which basically leads you to that conclusion. So you can check that and derive that for yourself. That you can show that actually for n qubits, now we are talking about not arbitrary particles, but specifically about systems of n qubits whose dynamics is governed by a Hamiltonian in that standard form, with the Pauli basis. These qubits physically could be spin 1/2. You could have an Ising magnet, and the elementary magnets are spin 1/2 with a magnetic moment, and you have some type of interaction which need not be local. You can have long-range interaction in your Ising system, and then this Ising system can also be described by, or the Hamiltonian describing the Ising system can always be cast in this standard form. And suppose you want to simulate the time evolution of this Ising system on a quantum computer. Now, the claim is that this is possible even in situations where the interaction is not local between the spins. However, there's another requirement, and that's a weaker requirement than locality. The requirement that is that the Hamiltonian is sparse, in the sense that the number of coefficients in this sum, which are non-zero, scales at most polynomially with n. So you can have contributions to the sum where in the tensor product you have all different Pauli operators for all the qubits involved. So that would be a highly non-local interaction involving all the qubits. But the requirement instead is that the number of non-zero contributions to the sum that scales at most polynomially with the number of qubits in the system. The circuit that does the simulation of such unitary evolution, time evolution, generally involves auxiliary qubits. We have encountered auxiliary qubits in various places, also in various algorithms. So these are qubits which are initially in the basis state 0, and at the end they are also in the basis state 0, but in between they couple to the other qubits and undergo transformations, and therefore they contribute to the successful execution of the algorithm. And this applies also, and in particular, to this problem of simulating quantum dynamics, that any circuit that does the simulation has not only input qubits representing the initial state before the evolution starts, but it also features auxiliary qubits that play a role in the simulation. And I would like to illustrate that to you with a simple example involving 3 qubits. And I would like to show you a circuit that affects the time evolution or a unitary transformation. Here I don't have the time variable t in the exponent, but instead I have an angle phi. Yeah, so instead of a time evolution, you could also regard this as a rotation in 3-qubit Hilbert space by some angle phi. Yeah? But you may just as well replace phi by time. Yeah, so we have in the 3-qubit Hilbert space, we have an evolution operator of this form. Yeah, and it's generated by a tensor product involving all 3 qubits. Yeah? Tensor product of 3 Pauli's. I claim that this unitary evolution is simulated by the circuit that you see on the right hand side. Yeah, so there you see that you have 3 input qubits. These are the 3 upper qubits. And then below you have 1 auxiliary qubit which starts in the basis state 0 and ends up in the basis state 0. In the first stage, sort of with a series of C-naughts, the input qubits are coupled to the auxiliary qubit. So you create sort of a non-trivial 4-qubit state. And then you have at the center a single qubit gate that applies only to the auxiliary qubit, and this U phi effects a rotation on the Bloch sphere around the z-axis by an angle phi. And that happens to the auxiliary qubit. And then to the right of that, you have a series of C-naughts which basically undo the initial coupling to the qubits. The claim is that the output state of the qubits of interest is the input state and then evolved with this exponent, with this exponential that I've written on the left hand side. Let me consider what happens if the 3 input qubits are in respective basis states x, y, and z, where x, y, z are either 0 or 1. And of course the overall transformation that is effected by the circuit is uniquely specified if I know what happens to arbitrary combinations of basis states. If you remember what the C-naught does, well, first of all, here the input qubits, they play the role of control qubits. So their states, if they are in basis states, they don't change at all during that sequence of C-naughts. What changes is the state of the auxiliary qubit. If you remember, mathematically, the effect of a C-naught on the target qubit could be written conveniently as an addition mod 2. So if the input basis state of the target is, in this case, 0, and the control qubit is in the basis state x, then after the C-naught, the target qubit is in the basis state 0 plus x mod 2, which of course is the same as x. After the second qubit, with the same logic, the target qubit is in the state x plus y mod 2. And after the third C-naught, it's in the state x plus y plus z mod 2. the rotation about the z-axis that follows by an angle phi, that affects the unitary transformation, which can also be written as e to the I Pauli z phi. Yeah, so this is the unitary operator, unitary transformation that is affected by this single qubit gate. Now, what is the effect of such a unitary transformation on a basis state? If this is applied to the basis state 0, the basis state 0 is an eigenstate of Pauli z with eigenvalue +1. So this gives then e to the I phi times 0. If instead it's applied to basis state 1, this is an eigenstate of Pauli z with associated eigenvalue -1. And therefore, when you apply the u phi, and you write it in this exponential form, then you see immediately that the effect is e to the -I phi times basis state 1. Okay. This can also be summarized. The effect of u phi on a basis state t is either e to the plus or minus I phi times t. Yeah, and whether it's plus or minus depends on whether t is 0 or 1. And one way to write it is to say this is -1 to the power t times phi. Keeping this in mind, we can say that after this single qubit gate, the auxiliary qubit is in the state e to the I -1 to the power, well, before the gate it was in the basis state x plus y plus z. So it's to the power x plus y plus z mod 2 times phi times the basis state x plus y plus z. And then the rest is really trivial because the C-naughts basically undo the initial C-naughts, and the auxiliary qubit ends up again in the basis state 0. The other three qubits, they haven't really changed during the entire circuit. Yeah. The only thing that happened is that overall we have acquired a phase factor e to the plus or minus I phi, yeah, where the plus or minus depends on this sum x plus y plus z. Yeah. So we can put it this way: the three qubits at the end, they are in the state x, y, z as before, but they have acquired a phase factor e to the I and then -1 to x plus y plus z times phi. Yeah, so this is really the effect of the circuit, that when the input qubits enter in basis states, then they acquire a phase factor e to the plus or minus I phi, where the plus or minus is given by -1 to the power x plus y plus z. The question is that what we want? If we look at the unitary operator on the left hand side that we want to emulate with this circuit, then again think of applying this unitary operator to a 3-qubit basis state. If say the 3 basis states are all 0, so they are all eigenstates of Pauli Z with eigenvalue +1, then applying the tensor product of 3 Pauli Z's to the basis state 0, 0, 0 gives +1. So then the exponential will give a phase factor e to the I phi, e to the plus I phi times the basis state 0, 0, 0. And if instead you apply it to the basis state 1, 1, 1, then if you look at the exponent, Pauli Z applied to basis state 1, that's an eigenstate with eigenvalue -1. So you get then, for all 3 qubits, you have the eigenvalue -1 times -1 times -1, which is -1. Yeah. So the exponential of that tensor product applied to 1, 1, 1 gives e to the minus I phi times 1, 1, 1. So there also you get phase factors of the form e to the plus or minus I phi, where you get a positive sign in the exponent if you have either no basis state 1 or you have an even number of basis states 1 amongst your 3 qubits. Or you get a minus sign if you have an odd number of basis states 1 amongst your 3 qubits. And once again, one way to write it is as -1 to the power x plus y plus z, where x, y, and z denote the basis states, mod 2, because this sum x plus y plus z mod 2, that is 0 if you have an even number of basis states 1, and it's 1 if you have an odd number of basis states 1. So it's, at the end, exactly the same effect as the circuit on the right hand side.